T2 demos. T2 demos. T2 demos. This is the first test to try to do time-lapse with the X-T4. There's the parameters. We're going 300 times. Speed up, these are JPEG frames. There's lots of problems with this, but it's fairly encouraging. I'm worried, since this is just one power zone, I'm worried about when we get to like 9 power zones, whether there's going to be enough res. But we'll see in the second demo where I do some camera projector automation, I'm calling it, that it looks pretty good. We can push from here, we can push all the way into a single tile after the fact and still like read the text, for example, which was not really true with the previous solutions. I don't know if that will still be true with 9 power zones, but we'll see. So this was a big update of almost everything, because I hadn't had this grid fired up for quite some time. I'd been working on the single ring, and then obviously just doing a Eugene run, which I wanted to run until it settled one way or the other all by itself, but I didn't really understand how the Fuji X-T4 works, and its battery died. So that's where this simulation ends. All right, so here we are pushed into a single video, also with a little bit of color grading, since the background of the CDM menus really should be brown, and the LCDs we're using are really so low quality. So I've just tried to get this to approximate, to sort of emphasize rendering what passes for true colors on the LCDs, and let the the T2 tile cases and the surrounding environment and stuff go hang. But I'm also and this is using the Kdenlive transform effect with keyframes that are set to smooth, which is cubic splines, I think, and I'm starting to get them working. You can see that this is actually fairly smooth, and it doesn't have a lot of changing in directions that don't make a certain amount of sense given the action on the screen. So this is it. This is the first test. I've now got an order for one of these dummy battery things that connects to a charger so that it's not relying on USB power. So hopefully we'll be able to do much longer. Lots more stuff to do. Just figured I'd put the first test up. That's it. We're ready as we're gonna be here. By step. So that's about as well as it got it to work so far. Hi, everybody. We are at Artificial Life Creation T+2, the multicellular menagerie. The goals for today was somatic cells. Stick around. That's what we just saw not really happening. To get the first Living Computation Foundation book published, talk about that, have more big fun. February was pretty busy, and there was a lot of successes, but there was a lot of frustrations. I probably didn't stop and enjoy the fun as much as I should have. I have to keep working on that. Okay, so the schedule. Last time, kill zombies, increase code density, did pretty well with that. To this time, somatic cells, body cells, we sort of did that. We obviously need what's coming up next, coordinated movement. Somatic cells, any cell of a living organism other than the reproductive cells. Okay, now that's pretty obvious when you've got trillions of cells like one of us, but when you're down at the level of single cells or small collections, the distinction between reproductive cells and every other cell is not quite so clear, but exactly that's what we were trying to do with the fins on the fish. In natural biology, there are these cell adhesion molecules. I mean, there's been tons of Nobel Prizes awarded for people figuring out how cells interact with each other, intercellular interactions, recognition, communication, and how they exert forces on each other so that they can stay together, unlike the fish that we've got so far. And, you know, the model that I'm using for that, or at least part of it, is this intercellular goo, which I said I would talk about this time, last time, and I'm still not going to talk about it a lot, but essentially what it is the diamonds that we had before, they sort of had this blue edge, and the new ones that you see in the opening video, they have this kind of brown and yellow stuff around it. That's the intercellular goo, and part of its reason for existing is to create a bigger buffer so that we can be aware of other cells rather than just trying to get so far far away we can't see them at all, because if we can't see them, we can't communicate with them. So we want to be close enough to have some kind of interaction while still having enough room to get away if things start going wrong. So that's the intercellular goo. That's going to have to develop a whole lot more than it has. Oh yeah, and this was something that I made up ages ago when I was having some tweets with Michael Levin. People tend to focus on the cells. People tend to focus on the neurons. But really, the intercellular interactions is so complex and so powerful that this is a little bit about what we're trying to do here. So, okay. And my Stream Deck is getting unreliable. I'm going to have to buy another one or do something else. Drivers and driving. So, when we talk about distributed systems control, and folks like me who are doing this sort of bottom-up stuff are very anti-centralized, top-down, fixed control structures and all that, and want to have this distributed system control. But nonetheless, it's still going to be the case that, if you want to get something done as a little collective group, there's going to have to be a single decision. And the classic example in the diamonds is growth and movement. If we're going to go east, we have to all go east. So there needs to be some centralized decision, some decision held in common, however that is established. And, in the way it actually comes down to it is that, even though it's distributed system control, there is a point of centralization for any given decision point. The real question is that central point fixed by the architecture and never changes, or is it more fluid? Can it be here, there, or whatever? So in the case of the diamonds that we've got, the diamond root, the Hg atom right in the center, controls growth and movement, which makes sense because it takes signals in from all the edges about, clearances and contacts, information from the goo, and it makes a decision and it broadcasts it out to the whole diamond, and they all go one way or they get bigger, whatever it is. But once we have that location where control happens, the controller can become the controlled. And that's what this driver is about. So now we've got this new API. I really want to call them APIs. I really want to change the pronunciation of API to API, but it's another story. A new API call, advise root, that the diamond controller does. It looks around itself when it's time to make a decision about movement or growth, and it says, is there a controller nearby to advise me? And if the advise root returns false, then we just go ahead and do whatever we were doing before. So I used this diamond controller to make a simple little driver for a diamond, and they are down here. So this is a comparative one. These things are identical until there's a reproduction. You probably won't be able to see it. There's a tiny little red dot here and over here next to the root in the ones on the bottom. That is the controller that's getting the delegated from the root saying you want to do something. And what this controller says is if I am a right daughter, I want to go east, and if I am a left daughter, I want to go west. So they spread out. And look at this guy. The being, this being is really trucking. Now, of course, once we have a left daughter of a right daughter and a right daughter of a left daughter, they're still pointing at each other. But nonetheless, these guys manage to distribute themselves a lot quicker than the traditional less motivated, just sitting there vibing diamonds that we had before. So that's an example of what's going on. And the fins on the fish are using these drivers to try to stay in the direction which is where they thought their mother was. And now, of course, there's all kinds of troubles with that not working out. And once again, I can't get back to my slides. All right, there we go. Big science. All right, much of what I spent the time on for the month of February was collecting data for the A-Life paper, for the A-Life conference coming in June or something. That the paper deadline is March 13th. The final extended, no more extensions, is 6 days from now. I got a lot of writing to do. But, if it's going to be a paper at all, we have to do an experiment. We have to gather some data, do some kind of case study. So the run on the grid that we actually saw starting last time in February has been going now for almost 28 days, something like that. Less than that, 3 weeks anyway, something. And so I wanted to reduce all that data and answer questions like how long do diamonds typically live? How many kids do they have? And so on. And the data to work with is the same data that we've been watching, the camera shots of the entire grid. So I spent a lot of time learning about Python and OpenCV, Open Computer Vision, a big library, and you see all these demos, out in the world, full self-driving, where there's boxes around everything, person, Starbucks, and so forth, where the computer has recognized all this stuff in the image. So I figured, how hard could it be to just recognize the diamonds? They don't have that much variation. Well, I'm not a computer vision person. And in the end, I ended up with this thing, which is actually a manual, semi-automated way of tagging the data. Now, this one, it's got all these numbers, 102, 127. Those are all just local IDs that have been made up. So if I create a new diamond, like here, 134 or something, and I can move it around, but I'll just get rid of it because there's nothing there. So all these diamonds down here, I labeled by hand, but we can watch the whole thing run. So this thing has now already been. So the idea is I label the births and deaths, so where everything starts out, and the tracking tries to keep track of the diamonds as they move, and it does an okay job, But if we can rewind it. And so this is what it looks like. Most of what's going on there is tracking that the computer vision that I wrote is doing. You can see in various places it doesn't track very well. Like this thing keeps getting the wrong size. It turns out that down in Lotus 4, for whatever reason, things are much more finicky. The diamond tracking keeps losing the grid and flying away, and so on. In any event, I've now gotten 20 days worth of data labeled and produced into spreadsheets and CSV files so that I can start answering the questions about lifetimes and fertility and all of that stuff. So that took a ton of time in refreshing my Python, so much so that now that I've gone back to Ulam, I keep forgetting my declarations and semicolons, thanks Python. Okay, so that's that. And finally, Companionate Caring. This is the book I've been talking about on and off for months and months and months, written by my dad. And here it is. We've actually got a couple of copies that have been printed and sent to us. This just came Saturday, I think. And here's my dad there. He died in 2008. He was a philosopher, an ethical philosopher, and this was kind of his magnum opus, really. And so I thought I'd just read a little quote from it so to get you the idea. Now, of course, folks that are following the T2 projects are not necessarily ethical philosophers, but I think we are a fairly special crowd, actually. So let me do this. This is from the end of Chapter 2, a section called Ethics as Networking. I already like it. Okay. We are morally estranged from our classical tradition. We no longer share its moral ideals, perfectionism, absolute goods, hierarchically organized society, personality conceived as a struggle between reason and feelings. But this does not mean we are immoral. We have a different set of values. It is not so much that we have rejected traditional values as that they have gradually become irrelevant to our lives, our hopes, and our problems. The society in which they originated no longer exists. So that's my dad. And at the moment, I've got copies printed, but it's not in Amazon, Walmart, Barnes and Noble, and so forth. So we can't buy it, and it's super expensive. I'm pricing it at $25 for this, little thing. It's not about the price per page. It's about wanting to know some more of the background and maybe being interested in that. And mostly from my point of view, it's just about having having my dad's stuff out there. I'm so proud of him. And so that's it. Next month, April 4th, the A-Life paper will have been submitted long before that, like 6 days from now. But hopefully we're going to get coordinated movement. Let's see if we can get the fins on the fish to stick to the fish, and actually be able to buy a copy, not in physical stores necessarily, but online, and have lots more big fun. And that's it. And thanks so much for dropping in, and I hope to see you in a month. All right. Well, that is that. So I will. Once again, hi, Queerdo. Do I know about goblins? I don't know about goblins. And yeah, all right, ethical philosophy. Yeah. Well, hey. Uh, uh, um, you know, if folks want to chat, I mean, I have lots of really while we're here. It's so frustrating that my buttons have become unreliable. You know, there's a clip from the chapter one on the back of the book that I think kind of sums it up, and maybe I'll read that too, just cause. The more common view of ethics is that we can gain satisfactions and we can do what is worthwhile, but the two do not overlap very much. This inherited metaphysics shapes our conception of what we can make of ourselves. My radicalism is based in my conviction that this classical metaphysics is wrong. Our ethics, our view of nature, our theory of human nature, and our conception of the good society have all been based on that faulty theory of reality, and they all need revision. So that's what the book is about. It really has a flavor of my dad. I guess I will take the break and get the render started as usual, and then I'll check back in and see if anybody is still here. There's really most of the month was on Python and data gathering and dealing with the book, actually getting this book real, and so the fins on the fish has really only been like the last 3 or 4 days. So I'm happy to have gotten it that far. But I also think, I need to remember that I'm not supposed to show only polished stuff. I'm supposed to show my work. And we're supposed to see all the airplanes collapsing and people trying to get into the air before, so that we can actually appreciate what it takes to get in the air later on. So, what the heck? We had plenty of failures in the first attempts to do cellular adhesion and coordinated movement like that. Okay. I will mute the mic here and go back to the screensaver, I guess, and then come back once I've got the rendering started. T2 demos. T2 demos. T2 demos. Okay, the render is started. I feel like demo scene kinship for this stuff a lot. Certainly, it's very compatible in the sense of being bottom up. You know, engineering, science is about truth, and engineering is about capabilities, and that's what demos are. The demo is an example of a capability that, here, I've actually made a machine. I've made a collection of matter and energy, whether it's bits or metal or whatever it happens to be, it doesn't matter. I've made this thing that does this thing by itself. And in principle, you could build a similar machine that would do something by itself as well, and off you would go. And, my mantra is, if it hasn't got a demo, it's crap.
Speed up these are JPEG.
Now, of course, so then we got, Dad's book, and, no demo, so I should be saying it's crap.
It's fairly,
but I make special different exceptions for abstract stuff. But, but the important point, abstract stuff is great, but abstract stuff needs to be a little bit humble, because it's not real. It's not an actual machine. There's this additional step. There's this implementation gap that any abstract stuff needs to be able to
previous solutions. I don't know if that will still be true.
Okay, maybe I won't talk over myself. But so the point is that doing science, doing mathematics, doing philosophy is coming up with arrangements of language, and the language, might be great language, might be good this way, bad that way, whatever it is, but an additional step is required to make it profitable, to make it a system that actually does something that I could deploy, except in the limited case of just parroting back whatever I heard. So, you can say, the universe began with the Big Bang. And I can say, I hear that, and I can go to someone else and say, the universe began with the Big Bang. But it doesn't do anything else for me, except that I am now part of the union of people who say the universe began with the Big Bang. But when I have a physical machine, a demo, like this, the bar and the circle connected to it, this is one of I always love machines that show a lot of complexity and very simple things. And this double pendulum that has a bar with a circle hoop pivoted on it at one end is great. It's like super complex, chaotic behavior from just spinning the thing once. That's a demo. That I can say how to do something with, build a sculpture for my living room or whatever. And so demo scene. Take the demo seriously, and a lot of the demo scene. At least, the part that I was familiar with, I was never really in it, is about, getting as much behavior into this tiny little space, into this tiny little machine, as you can. And that's fun and clever. So it gets aspects of both kinds of problems, of the sort of logical puzzle solving and unexpected ways to do things you wouldn't expect. But the point is, then it's an actual machine. All of that cleverness is now made flesh in electrons, in bits, and cassette tapes, and punch cards, and whatever the media of the demo scene machine happens to be. Anyway, okay. I'm surprised that the fans on the workstation haven't come on so far. That's nice. Life's simple pleasures. But so that's it. I am. I'll wrap it up here. 12:30, close enough. And again, folks, the folks that are here live. Thanks so much for actually finding a way to stop in. It helps me so much to know that there actually is this connection, this real time, almost real time, whatever YouTube gives us by default, down 20 seconds or something like that. But that is, I'm constantly thinking about the distinction between speaking and writing, and the important distinction, I think, and I've said this before, is that it's the hearing. That's what makes it talking, that there's somebody who's picking it up before there's a chance, when you can't do undo. When there's no sneeze button that you can suppress the microphone or whatever there is. And there is with the 20-second cap on YouTube, but I've got nobody manning the sneeze button or whatever it's called. So that's enough for now. And Guido, pushing the limits of what you can do within the limitation. Yeah, the demo scene thing. And one of the things that I find challenging about explaining the movable feast, super appreciated, Guido. Thanks so much. And one of the things that's tough about the movable feast machine is that, there are these tremendous constraints that all of the programming you're doing is within this tiny little event window, plus or minus 4 sites on this, potentially arbitrarily, indefinitely large grid of sites. And you have to figure out how to do it all, but break that all down so that little teeny decisions that can only see distance 4 can put together to do these giant diamonds, relatively speaking, giant diamonds that involve hundreds of those distances, acting in a coordinated fashion. And that is very much in the demo scene spirit, where you have these constraints from the physical. And the fundamental constraint that I'm committed to living with is spatial layout, that you only have local communication. And anytime you decide to cheat and say, I'm going to look at the whole tile, not just at my little sites, or I'm going to look at, everything that I can reach with Bluetooth or whatever it is, well, that's fine. But now you've got all of the consequences of putting communications in at that scale rather than just down at some smaller scale. And you haven't solved the problem. You've just pushed it off. And typically, in fact, usually made it bigger and worse, and that's a lot of where we are now. And now I'm on to my traditional computer security rant. Save it for another time. Anyway, hey, contemplation, decloaking off the port bow. How did I set on distance 4? This is way back in the prehistory, in the OOs, when we were looking at different architectures for the movable feast machine, and we had different atoms. So, for example, the P1 atom, which is the first one that was ever published, each atom was 64 bits long, and it had some sort of hard-coded definitions of bonds and stuff like that ended up feeling like a bad idea. So the P3 atom, which is what we've been using through to today, is the 96-bit atom. And no, hey, thank you for asking. So I played around with, distance 1, distance 2, distance 3, distance 8, and so forth. And, it's just simultaneous equations. The bigger you make it, the easier programming is, but the bigger the caches have to be to send updates back and forth between the neighbors, the more events will actually end up straddling tile boundaries if you have a big event window versus a small event window. And events that straddle tile boundaries tend to be much more expensive. So just like making the atom bigger makes the communication costs more expensive, making the event window bigger makes communication costs more expensive as well. And 4 ended up just sort of feeling like the sweet spot, like that. It was sort of the 4 went back to the P1 atom. I didn't consider changing it. Basically, I wanted to get something that was as small as possible that I felt I could actually program with. I could actually have some hope of doing some non-trivial programming stuff with it, as opposed to going with distance 1, which is what a lot of traditional cellular automata do. And like the von Neumann replicator, all of those CAs, those are distance 1, depending on von Neumann neighborhood or Moore neighborhood, whatever. But essentially, super tiny. Which is great as far as it goes, but it makes the programming a huge pain in the butt. So much so that much of the scientific results that come out of those, the mathematical, formal scientific results that come out of that cellular automata stuff, is basically explaining how to do basic operations given that incredibly tiny event window. like getting signals to cross, to be able to send one this way and one that way without having them interfere with each other, so that you can make wires to send logic through. That is non-trivial when you're doing the tiny little distance one event window. But for us, with event window 4, we can send stuff all over the place. We can send wires in 6 different directions, no problem, because we can make dotted lines with this big an event window. So that's it. I don't have an answer for exactly why 4, except that's what ended up feeling like the sweet spot between big enough to programmable, but small enough to keep the amount of communication cost manageable. Oh, no, thanks for asking. I feel like a dope sitting here. Any questions? But it's the same thing that used to happen in class, except for the fact that in class I was always blabbing all the way until the bell. So usually that wasn't a problem. But anyway, this has been great. Thanks so much, folks, for coming in and asking some questions, and thanks so much for being here. And then for all the folks that just watched the 15 minutes, that's great too. I will take it all. I really sort of feel like I should do a haiku version of it, summary of the thing. A 15-second version as well as a 15-minute version. Yeah, you too, Andrew. We'll catch up. We'll chat. So we'll see everybody again, I hope, in April. All right. That's it. This is great. Ending the stream now.